In this video, we will be discussing the area of rhombuses and kites. Now, some properties of rhombuses and kites that I wouldn't expect you to know right now, and I will give you on, let's say, a quiz or a test, are these three pieces. Rhombuses and kites have perpendicular diagonals. So what do we mean? We've used the term perpendicular before to describe the relationship that the base and the height must have in triangles. But the diagonals really go from one vertex to another vertex through the shape. So this is one diagonal in the rhombus. And I know this is a rhombus because rhombuses have four congruent sides. Okay? So this is the rhombus if we're color coding here. And so if I look at the other diagonal that's right here, then what I'm saying that these two pieces are perpendicular, which means they create 90-degree angles. So notice I already had one 90-degree angle drawn in here, but technically there are three other 90-degree angles you could draw in. Now, not only do rhombuses have perpendicular diagonals, but so do kites. And so here's one diagonal of the kite, and here's the other diagonal of the kite. And again, notice there's one 90-degree angle drawn in, but you can draw in three more 90-degree angles if you like. Now, how do I know this is a kite? Well, because it looks like a kite. Well, yeah, it looks like a kite, but by definition, a kite has two pairs of adjacent congruent sides. And so here's two sides that are adjacent and congruent, and here's two sides that are adjacent and congruent. And you might go, but wait, if a kite has two pairs of adjacent sides that are congruent, aren't rhombuses kites? Because don't they have two pair of adjacent sides that are congruent? And yeah, a rhombus is a type of kite, but we're jumping the gun here. We will get more in-depth into quadrilateral properties later on in the school year. All right, another property of kites and rhombuses that I will give you on quizzes and tests for rhombuses is that the diagonals, not only are they perpendicular, but they bisect each other. They cut each other in half. So this longer diagonal is going to cut this shorter diagonal in half, which is why I have these congruent markings on the shorter diagonals, two pieces, and on the longer diagonal, these two pieces are congruent to each other. So again, I will put those markings in the problems for you. Now, the kite, on the other hand, only has one diagonal that's bisected. And in my picture, it is this diagonal that is being bisected. And if things were drawn to scale, you could easily tell, hopefully, that this diagonal, that this little piece and this piece clearly are not congruent to each other. Okay? So all of these properties I will have marked for you in your pictures. So you don't have to worry about memorizing these yet, not until we get later on in the school year. So if we were going to focus with, say, a kite initially, and oftentimes, I will say, instead of giving you the side lengths of kites and rhombuses, typically we're going to be talking about the diagonal lengths. So notice AC, when I say this is 10, all the way from here to here is 10, do I know how much this piece and this piece are? I can't just assume they're 5 and 5. And so again, I would say that this piece and this piece are congruent for you in a problem. And so that's where the 6 is going to be useful. So if this whole thing's 6, how big are those two little individual pieces that apparently are congruent to each other? And they're both going to end up being 3s. Now, I'm also going to draw in the other 90-degree angles. There are 3 other 90-degree angles. At a first glance, you might say, well, hey, this kite really has 1, 2, 3, 4 right triangles in them. So can't we just find the area of those 4 right triangles? And we run into a problem if you think about them as 4 separate right triangles. And again, how long is this piece right here? And we don't know how much of 10 this is. And we don't have enough information to be able to figure that out. So instead of looking at a kite as 4 separate right triangles, we're going to look at a kite as 2 triangles. And we're going to look at it in such a way that we have to look at it as 2 triangles that will have the same area. Because if you now look at these two 3s, what do those 3s represent to these 2 triangles that I've highlighted in yellow and highlighted in kind of a pinkish red. And these represent the heights of the two triangles. Now, the base is really this whole diagonal. And how long was that whole base? Was 10. So who cares how much this little piece is of 10 and how much this little piece is of 10? Because we're going to look at it as the whole thing is 10. So now the area of this triangle is going to be 1/2 base 10 times height 3, which is going to give me an area of 15. But guess how much the area of this triangle is down here? It's also going to be 15. So what I will do, I mean, if you want to write out another area equals 1/2 10 times 3 and say that's 15, and then say 15 plus 15 is 30 overall, you can certainly do that. But I'm going to say the area of 1/2 of the kite is 15, and then I have two of these triangles. So I'm going to multiply this 15 by 2 and get that I have a total area of 30 units squared. So I'm going to break down a kite really into two triangles. All right, and then we're going to do 1/2 base times height. Now, there is a formula that's used for kites, but I'm not going to tell you what that particular formula is, because again, I've had students in the past try to memorize it and then they screw it up because they're not really thinking about the shapes that are inside the kite. So in terms of rhombuses and kites, I want you to think about them as triangles. And kites, we're going to focus as two triangles. We're going to talk about this triangle and then this other triangle that's going to have the same exact area. And in rhombuses, we have some flexibility. So I'll leave the triangle discussion for the next example. So here I've got a rhombus, and I know it's a rhombus because all four sides are marked with the same congruent markings. And I'm told that the right side's 10, so if you really, really wanted to, all four sides are 10. And I was also told initially that the diagonals are perpendicular. And so there's one 90-degree angle. So if you want to, we could draw in 3 more 90-degree angles. And the only other piece that I could really get right now is that if this piece is 6, then so is this other piece that has the same congruent marking. Now, in terms of these rhombuses, we could look at this as one right triangle at a time. And then each of these right triangles, all four of them are going to be exactly the same. So we could look at this as one right triangle and then multiply the whole thing by 4 to get all 4 right triangles to make up the rhombus. So I'm going to show you 3 different ways to tackle this one. Now, if I wanted to find the area of this triangle, and if we wanted to use 1/2 base times height, the base and the height have to be perpendicular. And hey, there's a right angle, so that means this 6 and this side are the base and the height. Now, we could call this 6 the height, but we got to figure out how long this piece is. And so if you realize we've got a right triangle and we know 2 of the sides, so couldn't we use Pythagorean Theorem to figure out how long this piece is? And so if you wanted to, we could call that side here x, and we could set up x squared plus 6 squared equals 10 squared, and we could have x squared plus 36 equals 100, and we could subtract that 36 over to the 100 and get 64, and we could square root both sides to get that that piece is exactly 8. Now, this also banks on our discussion of Pythagorean triples. A 6, 8, 10 is a Pythagorean triple in disguise because the greatest common factor of 6, 8, and 10 are all 2. And so if I right now thought about maybe I didn't know that 8, but if I took the 6 and the 10 that I did know and divided them by 2, we can see that we'd have a 3 something 5 triple, and this ends up being a 3, 4, 5 triple in disguise. And so we'd have to take that 4 and double it to get back to what it really should be, to the 6, 10 triple. So if you knew it was a triple, you could go ahead and call it an 8. If you didn't realize it was a triple, then you're just going to have to do the Pythagorean theorem. Okay? So now we know the base is 8. And so 1/2 8 times 6 is going to give me an area of 24. Now, there's not just 2 of these triangles, there are 4 of them altogether. So now I could say, hey, if I took that 24 and said I really have 4 of those triangles identically in this rhombus, then the area is going to be 96 units squared. Now, I'm going to get rid of the Pythagorean theorem down here, so hopefully you were done with that, and get rid of the triple talk here. But I'm going to talk about how we could extend this to make it more like the kite problem, right? Because in the kite problem, we combine two triangles into one. So imagine we looked at this triangle all together. And we could say, what if we could do 1/2 base times height with it? Well, the base is going to end up being this piece, which it's made up of an 8 and another 8. So altogether, this base is 16. And what's perpendicular to this 16? Well, it would be this 6. So let's think of it this way. Let's get rid of those pieces. Now we'll leave that there. So if we looked at this triangle, its area would be 1/2. The base is 16, because I'd add those two 8s there, and then times the height of 6. Well, that's going to give me an area of 48. Well, how many of these triangles do I have in the rhombus? Well, I've got one more on this other side. So I could say if I double that, that's going to give me 96. Perfect. Now, one other thing is, what if I looked at the rhombus as this triangle instead of the triangle that I just looked at? Well, now the base, let's grab a different color here. The base is really going to be this, and the height's going to be here, because that's the perpendicular relationship. So if I took that 6 and 6, well, now it's got a base of 12, and the height is going to be the 8 that I got earlier. So if I were to look at this green triangle, and I'll come down here now, I could say 1/2 base, which again is the 12, it's the two 6's added together, times the height of 8, and that's going to give me 48. Well, how many of those green triangles could I have in the rhombus? And I could have a second one right here. So if I said that times 2 triangles is also going to give me 96. So just know with rhombuses, you have a lot more flexibility. You can look at these rhombuses as 4 triangles, or you could group together 2 triangles and say that the other 2 triangles are going to have the same area. Or you could look at these 2 triangles with those 2 triangles, and they would have the same area. So I'll leave it up to you how you want to approach the rhombuses, as 4 little triangles or as 2 pairs of bigger triangles. Now, the last one again, I'm going to call a pause and try problem. If you want to try this problem by yourself, pause the video at this point and try it yourself. But I'm also going to show you how to do it right now. So again, if you want to pause and try it and then check your answer, that's fine, try it out. Now, this is a kite problem. So we're going to think of this as this triangle, and it's going to have the same area as this triangle down here. So I'm going to try to just use good old 1/2 base times height. And do I know the base or the height of these 2 triangles? And well, the only real numbers I know here are the 2 and the 12, which is going to represent the bases. But I got to think about that 2 and 12 added together. So really, I'm going to say the base of each triangle is equal to 14. I need to figure out what the height is. And here's what's going to be nice. The heights are going to be the same for both triangles because of that property of kites. Now, I'm going to have to use potentially some trig or a 30, 60, 90 relationship down here for this triangle. So I'm going to take this triangle and just blow it up a little bit bigger here. Just blow it up. So here's a 30. This was 2. Here was my height. Here's the 90-degree angle. Technically, this is going to be a 60. So if I wanted to use a 30, 60, 90 pattern, the side opposite the 30, this is my x side. The side opposite the 60, here's my x root 3 side. The hypotenuse is 2x. Which side of the 30, 60, 90 pattern do I know? I know the x side. X is 2. So sweet, what's the height? It's x root 3. Well, what's x? 2. So the height, do this in a different color here, the height is 2 root 3. But let's say you didn't want to use the 30, 60, 90 pattern. Let's say you wanted to use trig. So using the 30-degree angle, I know the 2, which is on the opposite side of the 30-degree angle, and I want to know the height, which is my adjacent side. So opposite and adjacent, I'd have to set up a tangent ratio. So I could set up tangent 30 degrees equals opposite 2 over adjacent h. And so if I wanted to solve for the h, for the height here, I could do what I call a flip-flop. And so I'd have h is equal to 2 divided by tangent 30. And if I plug that into my calculator, that comes out to be approximately 3.46 to the nearest hundredth. So now I could either use 2 root 3 as the height, or I could use the approximate value 3.46. And it doesn't matter which way you go here. So to give myself a little bit of room, let's go up to the top. So now let's go a different color. Area, and let's just use the green one here. The area of this triangle is going to be 1/2. Base, we said, was the 14, the 2 and the 12 added together. And it's either going to be 3.46 or 2 root 3. And I'll do it both ways, but I'll start with the 2 root 3. This is going to end up being 14 root 3, because really the half and the 2 knock each other out. And now, how many of these triangles did I have in the kite? I had 2 of them. So times 2 of these triangles gives me a total area for the kite of 28 root 3 units squared. So there's the exact area as a simplified square root. But again, if I wanted to look at this as the approximate with the 3.46 as the height, then I would say area, where am I at? Area equals 1/2 base 14 times height 3.46. And so if I type that into my calculator, I gotta actually type it in here real quick, I get 24.22. And again, that's the green rectangle, and I've got 2 of those. So I would say, let's take the 24.22 and let's double it. And so that's going to give me 48.44 as the area of the kite. But guess what 48.44 is as an exact answer? It would come from that 28 root 3. So again, there's your 2 possible answers I'd be looking for. 28 root 3 or approximately 48.44 or 48.4 if you wanted to go to the nearest tenth. And that is all for this video on area of rhombuses and kites.